In this supplementary video, we're going to be covering a rather niche topic known as Gaussian brackets. We're only using it for one very specific application, and it's not the most common way to even do that application, which is going to be convergence of continued fractions. We'll see that at the very end of the video. But for those 2 or 3 people a year who are looking for information on Gaussian brackets, here is something that you can find that will tell you some basic properties of them. So first, let's go over the notation. Suppose you have a finite list of numbers, a0 through an. The Gaussian bracket, where you put that list in square brackets with a subscript g, is just going to be another number defined based on the numbers that you plug into it. We're always going to be using integers, and in fact almost always positive integers, but any numbers at all will be fine. So we define the empty bracket, where you have that bracket with nothing in it, to take value 1. And if you have the bracket with a single number in it, it's just that number. Now this is just our sort of initial conditions for how the bracket operates. The real fire comes in its recursive definition. If you have a list of numbers in our Gaussian bracket, a0 through an, by definition, the way we're going to compute that is by pulling out the last term of the list, multiplying it by the Gaussian bracket of everything up to but not including that last term, but then adding in the Gaussian bracket that stops 2 terms prior. Notice that the first Gaussian bracket we compute is multiplied by the value an, but the second Gaussian bracket is just there by itself. It's being multiplied by 1. Okay, so let's look at an example. Compute the value of the Gaussian bracket 21534. So remember that the empty Gaussian bracket is presumed to have value 1, and if we just put the first number 2 in, that Gaussian bracket has value 2. From this point forward, we can begin using the recursive definition. So let's compute the value of 2, 1. So what we do is we take the last number 1, we pull it out, and we multiply by the Gaussian bracket of everything up to that point. Then we add in the Gaussian bracket of everything cutting out the last 2 terms. And since we only had 2 terms, when we cut out 2 terms, that's empty. We already know the value of this Gaussian bracket is 2, and the value of this Gaussian bracket, the empty one, is defined to be 1. So we end up with a total value of 3. And now we can keep going. The Gaussian bracket 215, we pull out the 5, multiply by the Gaussian bracket of everything up to that point. Then we add in the Gaussian bracket of cutting out the last 2 terms. If you excise the 1 and the 5 from the list, you're left just with 2. We just computed the value of this Gaussian bracket to be 3. This Gaussian bracket is defined to be 2, so we end up with a total of 17. And we're going to keep going in this way. So to compute the value of 2153, it's going to be 3 times the value of 215 plus the value of 21. We've already computed both of those. We get a total of 54. For the Gaussian bracket we were interested in, 21534, it's 4 times the Gaussian bracket 2153 plus the value of the Gaussian bracket 215. We've computed all these things and we end up with a total of 233. Now, unsurprisingly, because it has a habit of doing so, linear algebra shows up. Suppose you have a list, a0 through an, where n is bigger than or equal to -1, which looks like a very weird condition. We'll see what this means in a minute. The Gaussian bracket of that list is equal to the determinant of the following matrix. Now this matrix looks awful, but all we're doing is we're putting the terms of the list in descending or reverse order along the diagonal. Above the diagonal we put -1s, below the diagonal we put +1s, and otherwise we have zeros everywhere else. We're going to proceed by induction on n. Now look that our base case is actually n equals -1. Why is n equals -1 our base case actually going to make sense? Well, if n is equal to -1, then our list ends at an index before where it starts. Right? So if n is equal to -1, this terminal index is right before this one. That gives us the empty list. And remember that our initial conditions on Gaussian brackets start with the empty Gaussian bracket. So the empty Gaussian bracket has value 1, but then since we have no elements in our list, we have a 0 by 0 matrix here. And by convention, an empty matrix has determinant 1. So for n equals 0, our list has a single element in it, a sub 0. The Gaussian bracket just of that is that number, and then we have a 1 by 1 matrix where it just has that diagonal element a0. Its determinant is a0. That matches. Now, if you really object to n equals -1 being interpreted as it was, you can manually prove this for n equals 1 as well. The point is you just need 2 consecutive base cases so that you can proceed by induction having assumed that the result holds for 2 consecutive Gaussian brackets. So now let's compute the value of the determinant of the matrix given above, assuming that if our lists were only this long or this long, then the relevant determinants would be the value of the Gaussian bracket. That's our inductive step. Okay, so here's the statement of our theorem. Great. Now we're going to expand along the first row to compute this determinant. So on the first row, we extract this a sub n times the determinant of the matrix we obtain by striking out that row and column. So there's that. We're moving along the first row. So we started with a plus an. Now we have a minus 1 times the value of the determinant of the matrix obtained by striking out this row and column. Okay, so we have a 1, minus 1, 0, and then here is going to be a sub n minus 2, and so forth. So now we get the rest of that diagonal, but observe that this matrix, by assumption, its determinant is the value of this Gaussian bracket right here. Also, the second matrix, our first column, is a 1 followed by all zeros, so we can compute the value of this determinant by expanding along the first column very easily. So this matrix had determinant this Gaussian bracket. If I compute the value here, I would do 1 times the determinant of this matrix and then all zeros. Also observe that this minus minus became a plus, but then what was our second inductive hypothesis? That this determinant was exactly this Gaussian bracket, and what have we obtained? an times the Gaussian bracket going up to index n minus 1 plus the Gaussian bracket up to index n minus 2, that's the recursive definition of this Gaussian bracket here. So our main purpose in proving that the Gaussian bracket can be computed through that determinant is not because that's actually how we're going to do it, but to derive this result. The Gaussian bracket is symmetric. If you completely reverse the order of all the terms, instead of going from a0 to an, you go from an to a0, you end up with the same value. In general, you can't just switch values in between willy-nilly, but if you do this mirror reversion, you'll end up with the same thing. So the first Gaussian bracket is given by the determinant of this matrix, whereas the second one will be given by the determinant of this matrix. Now these matrices are pretty similar, but not identical. They're not transposes of each other, for instance. But suppose you wanted to compute the determinant of the second matrix. Rather than going along the top row, as we did in the previous theorem, let's go along the last column. So we'll get a whole bunch of zeros. Now you have to keep track of plus or minus ones, but remember when we do this expansion along a row or column, you start with a plus 1 here, and now you alternate minus 1, plus 1, minus 1, etc. But if you go diagonally, that stays plus. So plus, 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 plus. This is going to be a plus, meaning this is a minus. So what you'll end up with is exactly the same thing as if you had done expansion along the top row here or expansion along the last column here. It's a fairly quick inductive proof that these will be for any size the same determinant. Now, since the matrices have the same determinant, the Gaussian brackets have the same value. So the Gaussian bracket is symmetric. That's nice to know. Relative primality of terms. So two consecutive Gaussian brackets generated from the same list of integers, of course, are going to be relatively prime to one another. Specifically, the Gaussian bracket of a0 through an minus 1 and the Gaussian bracket a0 through an are relatively prime. The greatest common divisor is 1. So all we need to do to prove this result is find a linear combination of the two integers which is equal to either plus or minus 1. Specifically, we will show that the determinant of this matrix is negative 1 to a power. So here is one term we were interested in, and here is the other. And the determinant will be this times this minus this times this. So assuming these were all integers to begin with, these are all integer entries. So the determinant of this matrix will be an integer linear combination of these two elements right here. And if I can show that that integer linear combination of those elements is a power of minus 1, well then, the greatest common divisor of the two numbers must be a factor of this number, which means it has to be 1. So for n equals 0, here we have, in the upper right and in the lower left, we have the lists ending one index before they start. This goes from a0 to a minus 1, and this goes from a1 to a0. So those are empty brackets, and we've interpreted the value of that to just be 1. In the lower right, observe, however, if n is equal to 0, we start at index 1 and end at index minus 1. So now we have a list that ends 2 indices before it starts. We're going to give this special notation, just 2 asterisks inside, because it's really only ever going to show up here in this theorem. and we're going to declare that that has value 0. Under this convention, for n equals 0, we end up with the determinant of the following matrix. In the upper left, we just have a Gaussian bracket with one term, so that's A0. The other two empty brackets were given 1 as a value by definition, and this weird bracket that ends 2 indices before it starts, we're declaring to have value 0, essentially so that this works. And you end up with a determinant of -1 or -1 to the first. You can also, by the way, manually prove this for n equals 1 rather than n equals 0 and avoid this little hiccup of this Gaussian bracket that ends 2 indices before it begins. I just kind of like establishing it here. For those who are familiar with continued fractions, the appearance of this 0 will actually make sense. Now for n equals 1, we can compute the following. So here we have this Gaussian bracket, which you can compute to be A1 times the value of the Gaussian bracket just of this number, which is just A0, plus the empty Gaussian bracket of 1. Here, these are Gaussian brackets with a single term in it, and here's the standard empty Gaussian bracket. And if you compute the determinant here, you'll end up with this value times this minus this one times that. The A0, A1s cancel. You're left with a 1, which is indeed -1 to the second power. So let's assume the claim holds for some index bigger than or equal to 1. Now, what we want to show is that 2 consecutive Gaussian brackets are relatively prime. And so we are going to show that the determinant of this matrix is always a power of -1, and we've gone ahead and assumed that it works for some value of n. Now we just need to show that it works for the next value of n. Okay, so we let this list go 1 further, this one go 1 further, this one go 1 further, this one go 1 further. Now, if we go ahead and use the recursive definition of the Gaussian bracket in the left column, it's the last term times the previous list plus the list having cut out 2 terms, or the last term times the previous list plus cutting out 2 terms, etc. Now we can just compute the determinant, the upper left entry times the lower right minus the upper right times this whole lower left. Okay, after a few terms cancel, for example, an plus 1 times this Gaussian bracket times this one plus an plus 1 times this Gaussian bracket times this one. A bunch of stuff does indeed cancel. After a bunch of stuff cancels, what you're left with are these terms right here. But hey, the terms that we're now left with, if you factor out a -1, is itself a determinant of this matrix right here, which we inductively assumed had value -1 to the power n plus 1. We bring that -1 we factored out back inside. We get -1 to the n plus 2, which is exactly what we wanted. Now, what's the point of all this discussion of Gaussian brackets? For us, it's going to be the following result. Suppose you have a list, A0 through AN. Provided both sides here exist, they are equal. And on the left, we have the continued fraction A0 plus 1 over A1 plus 1 over A2, etc., etc. And on the right, we have the ratio of the Gaussian brackets A0 through AN by A1 through AN. Now, I say provided both sides exist because there's a possibility of division by 0 on one side or the other based on whether numbers are positive, negative, etc. So as long as we don't have a division by 0, both sides will be equal to each other. That's what we need to set out to prove. So we're going to prove by induction, unsurprisingly. Now, if n is equal to 0, our list has a single number in it. Well, the continued fraction is just A0, and then you stop, but that's A0 over 1, which is indeed the Gaussian bracket of A0 over the empty Gaussian bracket. And if n is equal to 0, this Gaussian bracket here ends 1 index before where it starts. That's our standard empty Gaussian bracket, which has, by definition, value 1. So for n equals 0, this claim is not very interesting. Let's assume then, inductively, that the claim does hold for some value of n. Suppose we make our continued fraction go 1 term further. Well, having made this continued fraction go 1 term further, what we have is A0 plus 1 over a continued fraction with n terms in it, A1 through AN plus 1. And we've assumed that n terms in a continued fraction can be expressed as the ratio of these 2 Gaussian brackets right here. But now I have 1 over a ratio as that second term, so we can just flip it over, okay? So with 1 over this ratio here, we flip it over. So this continued fraction is definitely equal to A0 plus this ratio of Gaussian brackets. Now, giving them a common denominator, we just have A0 times this Gaussian bracket plus this one over that denominator there. Okay, now we just have to do a little algebra. Okay, so in the numerator, we're going to use symmetry of the Gaussian bracket and the recursive definition. So here we have a naught times the Gaussian bracket a1 through an plus 1 plus the Gaussian bracket a2 through an plus 1. The first thing we're going to do is use our symmetry to say these Gaussian brackets can be exactly reversed. But now what do we have? We have a naught times a Gaussian bracket an plus 1 through a1, and then a Gaussian bracket an plus 1 through a2. That's exactly the recursive definition of the Gaussian bracket an plus 1 through a naught. Peel off the last term, multiply it by everything up to that point, it would be a1, plus the Gaussian bracket cutting out the last two terms, that would start at index n plus 1 and go down to index 2. But now this Gaussian bracket, I just use symmetry and swap the order again. So what we've shown is indeed this continued fraction is always given by this ratio of two Gaussian brackets, which is really the main point here. So suppose you have a integer a naught, and then you have a bunch of positive integers a1 through an. If you define p naught to be a naught, q naught to be 1, p1 to be a naught a1 plus 1, and q1 to be a1, in other words, p naught is defined to be this Gaussian bracket with a single number in it. Q naught is the empty Gaussian bracket. P1 is this Gaussian bracket. You compute this out, you get A1 times this Gaussian bracket plus the empty Gaussian bracket. That's exactly what we have here. And Q1 is this Gaussian bracket with a single term in it. Then what we do is we define recursively. Pn is given by an Pn minus 1 plus Pn minus 2, and Qn is given by the same recursive formula but with Q's instead of P's. Then what follows quickly is that since we started with these Gaussian brackets and we're doing exactly the same type of recursive formula, last term times something ending one index before plus something ending two indices before, that our Pn's and Qn's are actually computing Gaussian brackets. Specifically, Pn is computing the Gaussian bracket a naught through an. Qn, however, ignores a naught and starts at a1, going out to an. Then we have our standard way of computing continued fractions, which is starting with these initial values and then using these recursive formulas here. So the continued fraction a naught plus 1 over a1 plus 1 over a2, etc., is given by a ratio of two Gaussian brackets, but we now know those can be written as Pn and Qn, which is the standard way of defining them in the study of continued fractions. So in continued fractions, it's quite common to just define Pn and Qn recursively. And depending on exactly how much detail is going to be gone into, in an undergraduate course, it's usually just sort of brushed under the rug that you can compute a continued fraction in this way. What's worth pointing out is that if you were staring this continued fraction in the face, you wouldn't actually compute what it's equal to, naively just by hand, by working from a naught and working forward. You would start with an minus 1 plus 1 over an, you would simplify that fraction, then you'd simplify the next one, then the next one. You'd be working from the other end. Okay, you'd be working from index n back towards a naught. But in the study of continued fraction, where this list is then taken to go out and be infinitely long, it no longer makes sense to, quote, start at the end and work backwards, end quote. You will have to start at the beginning. So in the study of continued fractions, you need a way to compute your convergence, your Pn over Qn, starting at index 0 and working forward rather than the other way around in order to save a whole lot of work, and Gaussian brackets are the way to do it. Okay, so there is one method of proof that the Pn and Qn presented in the study of continued fractions actually work and give you your convergence of your regular continued fraction.